So, continuing our discussion on flow through a uniform duct, we have seen that the flow velocity at the two stations 1 and 2 satisfies the relationship u 1 u 2 a star square, or which can be written as m 1 star equal to 1 by m 2 star. There is a speed ratio at the two stations satisfies this reciprocal relationship, and which clearly shows that if m 1 star is greater than 1, then m 2 star will be less than 1, and if m 1 star is less than 1, m 2 star will be greater than 1, and vice versa. We have already seen that m 1 star become less than 1 when the flow is subsonic, that is when m 1 is less than 1. So, what we can see from here, that when the flow is subsonic at station 1, the flow is likely to be supersonic at station 2, and similarly, if the flow is supersonic at station 1, it will be subsonic at station 2. However, there is nothing in this relation that excludes this one of these possibilities. However, as we have mentioned that based on physical ground, that if there is some sort of non-equilibrium region between station 1 and station 2, where the viscous effects or the heat transfer is present, then through these dissipative processes, acceleration flow is physically not possible, and the jump from subsonic to supersonic is most probably will not occur in a real flow. However, we will later on show it using second law of thermodynamics that the deceleration from supersonic to subsonic flow is physically possible. However, the alternative subsonic to supersonic acceleration through this jump will not be possible. Using the relationship between the speed ratio and the local Mach number, which you have already derived and is given as m star square is gamma plus 1 m square by 2 plus gamma minus 1 m square. So, substituting this speed ratio at station 1 and station 2 in terms of the Mach number at station 1 and station 2, we get the relationship as gamma plus 1 m 2 square by 2 plus gamma minus 1 . which can be written in the form one plus gamma minus 1 by 2 m 1 square by gamma m 1 square minus gamma minus 1 by 2. That is, the Mach number at station 2 is simply a function of Mach number at the station 1 and of course, on the properties of the gas. That is, we can write that m 2 is simply a function of Mach number and gamma. You can see here that if m 1 is 1 then m 2 is also 1. However, if m 1 is greater than 1, this shows if m 1 equal to 1, then m 2 is also 1. If m 1 is greater than 1, then m 2 is less than 1, and similarly, if m 1 is less than 1, m 2 is greater than 1, which of course, we will see later on that will not be possible. Further, we see that as m 1 approaches infinity, a very large value, that is m 1 approaches infinity, then which is simply gamma minus 1 by 2 gamma, and thus m 2 reaches 0.378 if gamma is 1.4. The velocity ratio between station 1 and station 2 can also similarly be obtained as u 1 by u 2 as u 1 square by u 1 u 2, that is u 1 square by star square, that is using the continuity equation for the present problem. We all can also see that rho 2 by rho 1 is u 1 by u 2, and again can be written as gamma plus 1 m 1 square by 2 plus gamma minus 1 m 1 square. The pressure difference between these two stations can be obtained from the momentum equations written in the form P 2 minus P 1 equal to rho 1 u 1 square minus rho 2 u 2 square, which can be written as rho 1 u 1 into u 1 minus u 2, where rho 2 u 2 square is written as rho 2 u 2, which is equal to rho 1 u 1. That is, since rho 2 u 2 square is rho 2 u 2 into u 2, which is rho 1 u 1 u 2. Hence, we get the pressure rise P 2 minus P 1 by P 1 as rho 1 u 1 square by P 1 into 1 minus u 2 by u 1. Then, using the isentropic relation P 1 by rho 1, we can write this to be two gamma by gamma plus 1 the above velocity ratio as we obtained earlier. Substituting that velocity ratio and using rho 1 P 1 by rho 1 as A 1 square by gamma, this is the relationship that we obtained, which gives the normalized pressure rise. Also, the pressure ratio P 2 by P 1 then can be written as 1 plus 2 gamma by gamma plus 1 into m 1 square minus 1. The ratio delta P or P 2 minus P 1 by P 1 is often referred to as the shock strength. The temperature ratio can be obtained using the perfect gas relationship P equal to rho R T, that is P 2 by P 1 into rho 1 by rho 2, and this gives P 2 by P 1 is 1 plus 2 gamma by gamma plus 1 into m 1 square minus 1 into rho 1 by rho 2, which is rho 1 by rho 2 is 2 plus gamma minus 1 m 1 square by gamma plus 1 m 1 square, which can be written as 1 plus 2 into gamma minus 1 by gamma plus 1 square into gamma m 1 square plus 1 by m 1 square into m 1 square minus 1. Further, from the temperature ratio we can obtain the ratio of speed of sound at the two stations as well as the ratio of the enthalpy at the two stations, which are given as T 2 by T 1 for perfect gas. The limiting values for these ratios for AR with gamma equal to 1.4 limiting values of the ratios when gamma is a fixed quantity given by 1.4 as is usually used for air. We have already seen that M2 as M1 approaches infinity is 0.378 and the density ratio becomes approaches to a very high value. As the upstream Mach number reaches to very high value, the pressure ratio and temperature ratio also reaches a very high value. And looking back to all these relations, what we have seen is that for a thermally and calorically perfect gas, all the parameters are function of upstream Mach number and the specific gas ratio gamma. Now, computing the change in entropy between the two stations, you can write the change in entropy between the two stations is 2 minus S 1 is C p log T 2 by T 1 minus R log P 2 by P 1, which can be written as R log and substituting this pressure ratio and density ratio in this relation, we have S 2 minus S 1 by R equal to log gamma by gamma plus 1 m 1 square minus 1 since the flow process that we have considered here is adiabatic. So, S 2 must be greater than or equal to S 1 since the flow is adiabatic, and the relation it shows here that if m 1 is less than 1, then S 2 minus S 1 by R is negative, and this condition is satisfied only if m 1 is greater than 1. And if m 1 is less than 1, S 2 minus S 1 by R is less than 0. If m 1 is less than 1, S 2 minus S 1 will become less than 0, which is that is, if m 1 is less than 1, then we will have a decrease in entropy in the downstream, which is of course not possible as far as second law of thermodynamics is concerned, and hence we see a mathematical proof that a jump from subsonic to supersonic flow is not possible in this case, or that is through a shock a jump from subsonic to supersonic flow is not possible. And the only possibility is from supersonic to subsonic jump. A shock is called weak when the pressure rise across the shock is very small, and looking to the pressure ratio relationship, we can see that happens when m square minus 1 is small. That is, a shock is weak and when this shock is weak, that is when m 1 square minus 1 is small, the change in entropy can be approximated the change in entropy then can be approximated or in terms of pressure ratio gamma plus 1 by 12 gamma square. or see that for a weak shock the change in entropy is third order of shock strength. That is, and in the limit of a very weak shock, then we can say that change in entropy is almost negligible and it is the process is almost isentropic or nearly isentropic. Since the flow across the shock or the flow in this situation that we considered is adiabatic, we have T 02 equal to T 01 as the flow is adiabatic. T 02 is T 01 and the pressure ratio, the stagnation pressure ratio can be obtained in terms of the entropy difference and which can be written that P 02 by P 01 to be 1 plus 2 gamma by gamma plus 1 m 1 square minus 1 the power 1 by gamma minus 1 into gamma plus 1 m 1 square by gamma minus 1 Since change in entropy is directly proportional to change in total pressure, hence the total pressure is change in total pressure is also of third order in shock strength. Here this shock strength or shock jump relations we have expressed in terms of upstream Mach number. However, often they are expressed in terms of other parameters, particularly in terms of pressure jump instead of Mach numbers, and in general the shock jump relations are known as Rankine-Huguenot relationships. So, considering the flow through a uniform duct, we have seen that for a compressible flow through a uniform duct, if we have a supersonic flow at station 1, then we can have a subsonic flow at station 2. And since we have used integral relationship at station 1 and station 2, any non-equilibrium region is possible between station 1 and 2. Only requirement is that flow at station 1 and station 2 must be in equilibrium, and non-equilibrium region may exist between station 1 and station 2. Since the station 1 and station 2 and the region between them has no restriction in size, that is the non-equilibrium region can be of infinitely thin extent, we can consider that station 1 and station 2 may be just the two sides of one thin line, and in that case that thin line is called as the shock wave. As we have mentioned earlier that in real flow this shock thickness cannot be 0, there will be a finite thickness even though very small, and within that region there will be very large and rapid changes of the flow parameters, velocity and temperature, pressure and density. And these rapid changes in velocity gradient and temperature gradient give rise to these dissipative forces, and which causes a increase in entropy across the shock. Since we have considered one dimensional flow and the shock is standing across it, that is a normal shock, and in one dimensional flow that is the only possibility of a shock wave, a normal shock. And these normal shock relations that we have derived here are based on or assuming that the shock is stationary and the fluid is flowing through it with a speed u 1 on upstream and u 2 on the downstream. However, in all many practical problem, the shock is found to be propagating through the fluid. As you can think about that, if when an aircraft moves, the shock system of this aircraft or the wing also moves with it, and in that case the problem becomes a moving shock, and we would like to revisit this shock relationship for a moving shock. That is, when the shock is propagating through the fluid through a speed u s. That is, let us consider now a moving shock wave problem. Moving shock wave problem. Let us say we have a duct and we have the shock moving with speed u s. And as the shock moves with the speed u s, the fluid behind it, that is the fluid in this region, is also being dragged with it, and let us say that the fluid behind it is moving at a speed u b, and let us say that the fluid in front of it is stationary, that is the shock is moving through a stationary fluid, and we would like to see in this case the relationship of the flow parameters or fluid properties in station A and station B. Now, what we did earlier, that we satisfied the conservation laws, that is namely continuity, momentum and energy equation between the two regions at one ahead and one behind the shock wave. Now, we see that we cannot do that in this problem. We cannot satisfy the continuity equation between station A and in a region A and region B, simply because that the fluid in region A is not part of the fluid that is flowing through region B. It is always separated by this shock. However, what we can do in this case is we can consider a change in reference system in which, let us say we consider an observer who is moving with the shock. Let us say in this case an observer who is moving with the shock wave. Then with respect to this observer, then with respect to this observer, the fluid in region A, which we will now designate as region 1, is moving with the speed u1 to this direction, and fluid in region 2, that is B, is moving at a speed u2. This is with respect to an observer moving with the shock. Now, in this configuration, of course, we can, and the shock is stationary. The shock is stationary. Now, in this configuration, of course, we can satisfy the conservation laws between a station in region 1 and region 2, because now the fluid in region 1 and region 2 are part of the same flow. Now, what we find here, that u1 equal to us and u2 equal to us minus ub, which is u1 Now, the static densities, pressure and temperatures on either side of the shock, they are of course not affected by this transformation. The shock jump relation for these quantities, that is density, pressure and temperature, remains same as we have obtained earlier. The jump relation in this case are may be written in terms of shock speed and the speed of the fluid behind the shock, and using the transformation. The shock Mach number we can define as Now, using the pressure ratio, P2 by P1 as 1 plus 2 gamma by gamma plus 1 m1 square minus 1. We can obtain the shock velocity in a perfect gas. The density ratio and temperature ratio similarly can obtain by the Rankine-Hugoniot relationship, that is rho 2 by rho 1 and u 2 by u 1 also remain same in terms of m 1, and using the value of m 1 as obtained from here, this in terms of pressure ratio we obtain them. Similarly, we can write the ratio of the temperature, the flow velocity behind the shock, that is u b can be written as u 1 minus u 2, which can be written as u s into 1 minus u 2 by u 1. and in terms of the pressure ratio, this becomes Q 1 by gamma these static quantities, as you have mentioned that in same for both the system. However, when you come to the total quantities, they are not same in the two system, and say it should be noted that in coming back to that configuration 1 and A and B and 1 and 2, it can be seen that the total quantities at region A are same as the static quantities at region A, because the fluids there is stationary, that is H 0 A is same as H A. However, this is not same as H 0 1. H 0 B, that is the stagnation enthalpy in region B, is simply the static enthalpy at region B plus the kinetic energy of the fluid in region B, that is half u b square. However, this is not same as H 0 2, total enthalpy at 2, and also the total enthalpy in region B is not same as the total enthalpy at region A. However, the total enthalpy in region 2, which is simply H 2 plus half u 2 square, that is equal to H 1 plus half u 1 square equal to H 0 1. And using this relationship, the total quantities or the stagnation quantities can be found behind and across the shock. A shock will be called a weak shock if the normalized pressure jump is very small. That is, a shock is weak. Shock is weak when P 2 minus P 1 by P 1, that is the normalized shock jump, is very small. The disturbances are also then very small, and they can be obtained by expanding this relationship in series of delta p by p 1 and retaining only the first order terms, and this gives the density rise to be gamma minus 1 by gamma into delta p by p 1. The shock speed will be approximately u 1 into 1 plus gamma plus 1 by 4 gamma that is, the speed of a very weak shock is very close to 1, very close to 1, sorry, very close to A 1. For a very strong shock, this P 2 by P 1 is very large, there is very strong shock, that is P 2 by P 1 is very large. And in that case, rho 2 by rho 1 approaches as before, gamma plus 1 by gamma minus 1, T 2 by T 1 approaching gamma minus 1 by gamma plus 1 into P 2 by P 1. The shock speed approaches A 1 into gamma plus 1 by 2 gamma into P 2 by P 1 to the power half, and u b, that is the flow velocity behind the shock, is A 1 into So, in our discussion of flow through a uniform duct or flow through a normal shock, we have seen that when a supersonic flow crosses a normal shock, its pressure increases very rapidly or pressure increases by a jump, and in the limiting case of a perfect gas with gamma equal to 1.4, the pressure jump can approach very high value. Similarly, the density also undergoes a very rapid or very jump, and the limiting value of the density jump can be 6 for perfect gas with gamma equal to 1.4, which is usually chosen for air. The downstream Mach number become subsonic, and across a very strong shock, the downstream Mach number approaches a limiting value. For air with gamma equal to 1.4, the value become 0.378. We have also seen that the second law of thermodynamics excludes the possibility of a jump from subsonic to supersonic condition, meaning that shock cannot occur in a subsonic flow, and through a shock flow cannot accelerate. Accelerating shock is impossible as dictated by second law of thermodynamics. We have also considered a moving shock problem, where the shock is moving at a certain speed through a stationary fluid, and we have seen that the shock then induces a velocity to the fluid which is behind it, that is the shock sets the fluid behind it into a motion and raises its pressure and density, temperature. The ratios of the temperature, density and pressure, that is all the static quantities, remain unaltered as in case of a stationary normal shock. However, we have expressed this relation now in terms of pressure. Further, we have seen that the stagnation quantities are in the two configurations are different, and we have given how the stagnation properties in the two regions can be computed. We have also found the limiting values for the density, pressure and temperature rises, as well as the shock speed and the flow velocity behind the shock. what we have seen particularly today, that a moving shock or a disturbance sets the fluid in motion. However, how this motion develops, that is what we will try to see next in our next lecture. Thank you.